Back again. More 4.3. We're learning how to actually graph some shit, huh? Where's those peaks and those valleys at? What are those heights? Where are they occur? Yeah, where's shit increasing and decreasing? Where's it not increasing and decreasing? Right? All these questions. I know you just sit at home all day long just wondering how, why. Well, finally you're gonna find out. Huh? So we're gonna go ahead and find some local extrema. Just basic shit. You know what I mean? Like maybe you got a graph that looks like this. Like, hey, look, peaks and valleys and shit. What's the height? Things like that. We're gonna go through. We messed around that 4-1. We got this shit down. We can do it. All right, let's get into it. So let's pass through. Like we messed around with increasing and decreasing last time, but now we're gonna get down to what's called the first derivative test. So let's read through it. It's really not that exceptional. I think we'll be fine. Now, the first derivative test for local extrema. Extrema. I don't even know if I'm saying that right. Is it extrema? Extrema. Big shit. Small shit. The most, right? Extreme. Yeah. Suppose that C is a critical point. Remember the critical points? Take a derivative, set it equal to 0, or the derivative doesn't exist at that point, right? No, C is a critical point of a continuous function f. Remember, continuous function. And it's differentiable at every point in some interval containing C, except possibly at C itself, moving across this interval from left to right. And that's that same shit. Remember, we keep saying it. Closed interval, continuous. Differentiable on the open interval. Well, it's the same shit, just a continuous function. Smooth and continuous. All right, so 3 things. And this is common sense. This is duh shit. I'm telling you, this is duh shit. You got this. It's just all the freaking wording makes shit seem weird. So, if our derivative changes from negative to positive, then you have a minimum. Think about this. You have a derivative. Here we go. If it's negative, we're going down, right? And now it changes to positive. Doesn't that mean there's some shit down at the bottom? There's got to be a freaking minimum, doesn't it? I'm just thinking when it goes down and then it goes back up. Isn't that like a valley? All right, whatever. Maybe I'm just crazy. Let's keep going. Well, actually, I know I'm crazy, but whatever. Moving on. If f prime changes from positive to negative at C, right? So it's increasing, and then it flattens out, and it starts to decrease. I'm going to guess that might be a freaking max. You know, like, I know calculus is tough here, but being able to read it, just think. Here we go. We're taking off. It's positive. It's positive. Now it's going to change to negative. Now we're decreasing. It's like the top of a freaking roller coaster. So there we have it. All right, I think we got this. Now, the last piece. So if f prime does not change at C, that is, if it's both positive on both sides or negative on both sides, then it doesn't have a local min or max. So maybe it's like one of these. I'm going to go up to the top. It's going positive, 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 positive. We flatten out, not positive. There's no extreme value. I hate saying the word extreme. Sorry. There's no value. There's no local min or local max there. We flattened out, but it kept going because the thing never turned around and went from positive to negative. So we needed to go from either negative to positive or positive to negative, and then we have some local min or local max. So we can't just say taking the derivative, setting it equal to 0 has to be a local min or a local max. That's not true. But if it changes from negative to positive at some value, then you got a minimum. From positive to negative, you got a maximum. Let's do a problem. We're going to find all local maxima and minima for f of x is equal to 4x cubed minus 9x squared minus 30x plus 1. This one's nice and cooked up. Let's go get it. So our first step is we want to go and check and see where the derivative equals 0. That's how we're going to be able to interval test. Again, if you know that this is a cubic function, it's very, very freaking easy to do it. We don't need to use all this freaking interval testing. That is a cubic function. It's got a positive in the front. Positive, cubic. Guaranteed it does something like this, or it does something like this. It's a cubic. You learned this shit in college algebra. Maybe you remember it, maybe you don't. But if you do, you don't have to do any of this interval testing because you'll know what the F it looks like. All right, moving on. And granted, since I know y'all are going to be at home, you'd use your Desmos, check shit out. Cool. I'm going to ask you for exact answers when you do these things, and Desmos is not going to yank that out. The only way you're going to be able to do that is by going through and taking derivatives, setting them equal to 0, and solving on these things. So you are going to need to have a little bit of a knowledge of it, and remember, we will be back in a classroom eventually. You will need to know what a graph looks like, unless maybe you're one of those that's lucky enough to be able to get out of here after a Calc 1. Then good on you. All right, moving back. Let's take a derivative, set it equal to 0, and solve. We get 12x squared minus 18x minus 30. And now let's set this thing equal to 0 and solve. And while we're doing this, like, I hope we got some number sense enough to know that we can yank a 6 out of here, huh? That leaves us with 2x squared, minus 3x, minus what, 5? Is that what we got going on there? I think that might be it. And when we factor it up, I'm assuming you all know how to factor, huh? This is going to end up being 2x and x. Well, that's a 5, and there's that 3, so I think this needs to come over here. That needs to be there, and then the signs. This one needs to be negative, and this one needs to be positive. Hey, there we go. We solved for it. So let's set our factors equal to 0. All right, we got 3 factors, 1, 2, and 3. Well, we already know that 6 doesn't equal 0, so we won't look at that shit. So what do we have? That our x is equal to 5 halves and our x is equal to -1. Cool. Cool. We have now found the values where the derivative equals 0. We now found where the derivative equals 0. So I'm just going to make a little boundaries here. Just going, all right, cool. X equals -1. And then we have x is equal to 5 halves. Just right here on these boundaries. Just making up some boundaries. So we want to see, does it go from, now I'm just writing random shit in here, does it go from negative to positive to where we would have a minimum there? Right, it would say we'd have a minimum if it goes from a negative derivative to a positive derivative. We're just interval testing. We're testing the x values in between. And we'll just check. So we'll use our idea here, huh? Back to our first derivative test. Negative to positive derivatives. Let's jump back. So let's check our f primes. We have f prime up here. There it is. Look at it in all its glory. So let's check some stuff. Let's check f prime of, let's a number smaller than -1. And the answer is -2. Or anything really freaking simple, okay? Anything really simple. So pop in -2 right into there, because -2 is smaller than -1. And we go, we pop that shit out and we go, it's equal to a positive freaking number. Not equal to a negative number, just putting it in. I'm going to do one of them. Boo. So we'll have f prime of -2 is equal to 12 times -2 squared minus 18 times -2 minus 30. That shit is positive when you go through 4 times 4, 12, 48 plus 36 minus 30 is equal to a positive freaking number. We don't give a shit what the number is. All we care is that it's positive. So we have found from the interval from negative infinity lives over here, up to -1, we're positive. Now we need to plug in a value in between -1 and 5 halves. What is the number we are plugging in? And the answer is you're plugging in 0. It's the easiest number. We want to go easy. You get any choice of number you want to plug in. Let's choose the simplest frickin' number we can come up with that's in between -1 and 5 halves. And all we care about, we don't give a shit about anything here except for its sign. And this thing is equal to, when we plug that in up here, 12x squared, just cover up everything with the x's. You're left with -30, and we find out that we have it's equal to frickin' negative. I don't care what the number is. It actually equals -30, but we don't, again, I think you're catching the point. We don't care what the frickin' number is. We just want to pop it in. So now we need to choose f prime of some number that's larger than 5 halves. 5 halves is equal to 2.5. So you know what number we're plugging in? We're plugging in 3. We want the simplest of freaking numbers, the easiest of numbers, because you're not always going to have a calculator at home. We plug this in. Oh shit, it's positive. And there we have it. We ended up with a positive, negative, positive. So what does that mean? Well, according to back here in our thing, if we go from positive to negative, which is our first case, from positive to negative, we have ourselves a little bit of a max, right? Let's think. Positive to negative, then negative to positive. Wait a second. I think we got this one. I think we can figure this thing out. And if we just knew what the shape of a frickin' graph looked like, we would have already known exactly what the interval was. So since we go from positive to negative at -1, we have ourselves a max. So f of wrong color. F of -1, which is equal to, when you plug it in, is equal to 18. Sorry, is a local max. And if you were to just say f of -1 was a local max, that'd be fine. And now we could say that f of, and we got to plug in our 5/2, right? We'll find out what that is. Oh, found it. It's -271/4, clearly, right? But we've found it, and that is our local min. That would have been our valleys and our peaks. Because we already know the parent function of a cubic function, we wouldn't really need to do all this interval testing. We know the shape of the graph looks like what we have over there on the right. So we found our solutions. We went through and we found a local max. And we found a local min. Now, if we were to play this same game real quick, and we'll be done with this one. We were to play the same game, and let's say that we have some g of x that's just equal to x cubed. X cubed just looks like this. Notice there is no local min or local max here, because when you take a derivative on it, you get 3x squared. Now, if you are to plug anything into 3x squared, in anything, any value of x into 3x squared, this is always greater than or equal to 0, which means it never changes from positive to negative. So just because a derivative can be set equal to 0 and solved does not mean that we have a local min or a local max. So this is how we go through it, finding local minima and maxima. See you soon.